Shall we start the program, sir?
So, can we start?
Shall we start the program, sir? A very pleasant afternoon to everyone joining us the fifth international seminar organized by Global Research and Development Professional Society. We are delighted to have you all here with us in virtual mode. To behind today's program, I would like to invite Abhinav sir, Department of Publication and Production, Minority and Publication Press, to deliver the welcome address. Welcome, sir.
Good afternoon to everyone present here. On behalf of Leila Nikati Publication and Press Madurai, I am delighted to welcome you all to the 5th International Seminar organized by the Global Research and Development Professional Society. Today's seminar on highly isolated MIMO and frequency reconfigurable filtering antenna design for 5G communication brings us together to explore innovative ideas in advanced wireless technology. We are honored to have our esteemed research person, Dr. Atanu Chowdhury, with us to share his valuable insights. I thank all participants for joining this season and wish you a productive and enriching learning experience. With great pleasure, I welcome you all to this seminar. Thank you.
Thank you, sir, for the warm welcome. Next, it is my privilege to introduce our esteemed resource person for today, and sir, Assistant Professor, ECE Department, Calcutta Institute of Technology, West Bengal. He will enlighten us on the topic. Sir, we are honored to have you with us.
Hello.
Welcome, sir.
Okay, very good afternoon. Shall I start?
Yeah, yes, sir. Start, sir.
Okay. Good afternoon to all the participants. I think my screen is visible. So
Yeah,
welcome.
yes, sir. Listen, sir.
Yes, thank you. So welcome to the uh, seminar. So today my topic is highly isolated MIMO and frequency reconfigurable filtering antenna design with high peak gain for 5G communication. So in recent modern age, we are living in the 5G era, coming up from first generation, second generation, third, 3G, 4G, and now we are dealing with the 5G. So all these communications not only depends on um, not only for mobile phone, but also we can apply it in various sectors that we are concentrating on smart cities. So in smart applications, we can use 5G, or rather, in future we will also use 6G. So design antenna for 5G is also very crucial for today's research in that microwave antenna domain or wireless communication domain. So these are the outlines of that importance, and I will also show some of my works related to that. So before that antenna, so we have to know what is microstrip antenna. That is MSA, which nothing but it consists of a metallic patch that is a conductive element that with the current will flow through there, printed on a grounded dielectric substrate. That dielectric substrate does not, uh, it is not a conducting material, but the dielectric material, and below that substrate there will be a ground plane. It will be again a conducting material. Generally, for low frequencies, the conducting material is copper, but in higher frequencies, many materials are used for even for 6G, some graphite materials or say any conducting material, or The copper, maybe liquid copper, is also used nowadays, and it is commonly used for compact, low-profile wireless communication design, and it is very tiny in size. And it is available in various shapes like rectangular, circular, triangle, dipole, elliptical, anything in based upon its application, based upon its radiating frequency, based upon its bandwidth. There are so many applications of this microstrip antenna. We generally use it very commonly in our smartphone or mobile phone, and it is also used in radar, satellite, mobile, and wireless communication, even in some sectors of healthcare as also. Now, this is a microstrip patch antenna. This is a basic formula for square shape or rectangular shape, very commonly available, that what will be the width of the antenna depending upon the resonant frequency. This FR is the resonant frequency in which the antenna will work. V0 is the speed of the light in free space, and epsilon R is the dielectric constant of this substrate. So you can see, depending upon the application or depending upon the frequency at which we intend the antenna to work, we have to determine both width and also the length of the antenna. And that is the equation for the effective dielectric constant. And this del L, you can see this some arrow symbols are there in the patch, where actually the from this edge the radiation of the antenna takes place. So here a small increment of the effective length gets increased here del L, and also this part in the backside del L. So it becomes twice of del L, which is actually the we can uh, we just reduce the length in calculating that length of that antenna. This is due to the effect that is called fringing effect. This radiation takes place through the edge of the antenna. Now, this square shape or rectangular shapes, it can be in different shape, but this patch is need to be fed. Different fitting techniques are generally used. Like first one is my microstrip line fit, which is very much common um, in that antenna design domain. There is a probe fit from the bottom, that is ground plane is cut, and the probe is there is a conducting element through the probe is connected to the patch. Then there is aperture coupled field, where two different substrates are used, that is substrate 1 and substrate 2. In between there, a ground plane is inserted, and the patch is above the substrate 1, and this ground phase or this from this uh, between the substrate 1 and substrate 2, the ground plane is fed to the patch through midway of the substrate. And another is called proximity coupled feed. There is again two substrates are used, but no ground plane is inserted between them, and there is microstrip line is there to feed the patch. Now, what are the advantages of this microstrip antenna? These are very much low profile, lightweight, easy integration with the planar circuits, suitable for airborne and satellite-based platform, and also frequency range compatible for meteorological applications. We uh, first determine which frequency we need to use. Then using that frequency, again I'm going back, using that frequency we determine the width and length. Also the height of the substrate is determined, and which dielectric constant material we need. We just derive it from this resonance frequency, and then we design it. What is the design process? First, again, I have already stated that the substrate and material we have to select from the resonant frequency calculation. Then, after all these frequency selection, substrate material, we just use simulation tools like HFSS and CST. I do prefer ANSYS HFSS, that is high frequency structure simulator, which I generally using which I generally use to design the antennas. And after all the optimization and were all done in the HFSS, that is after the successful simulation, we do fabricate the antenna, then test it using a VNA, that is the picture of a VNA, that is vector network analyzer, which determines the frequency and bandwidth of the antenna. Then anoic chamber setup. This one is the picture of an anoic chamber. Here we use what we measure. We measure the far field and near field radiation patterns, gain, directivity, radiation efficiency. These all the parameters are measured here. Now I am coming to the today's topic. That is why 5G communication I have chosen in today's seminar. Here you can see in the diagram we have come through various ages of generations. In 1980s there was 1G. That is only voice call, no mobile connectivity, analog voice call. In 2G, there comes digital voice call in 1990s, and text messaging and basic data service are also there with an maximum speed of 1 Mbps. Then in 2000 era, there is 3G mobile broadband, introduction of smartphones, and the speed also get increases. In 4G, we can get up to a maximum of 1 Gbps and fast mobile broadband using internet protocols. Nowadays, we are living in 2020s and expecting in next 5 or 6 years to get the 6G over that. So enhanced mobile brand and wireless for industry, and we are moving towards smart cities. At the maximum, we are reaching a 10 Gbps of internet speed, even in motion, not in static, even in motion. Means when we are inside a car, we can have a speed of maximum 10 Gbps. That is crucial in our very fast-paced society as well. And in designing these 5G antennas, there are some challenges will be there, like power limits or finite spectrum available. Our government have to buy the spectrum for each and every band. So we have to design this antenna in that given spectrum ranges. We cannot go out of it. And a 5G antenna also requires balancing data rates, isolation, and polarization, especially when we are switching between different frequency bands. Now, design context of 5G antennas, we have to keep many things in our head, that we have to enhance the speed and connectivity, diverse application like healthcare, transportation, manufacturing, globalization effort. Obviously, the all researchers throughout the globe, we need to upgrade this 5G technology for high-speed communication to reach that 10 Gbps data speed. What are the challenge? That is, I have already shared that the finite spectrum available for 5G, and we have to carefully manage this, and we can innovate whatever we want to do. Some motivation. 5G actually divided into three parts of bands, that is low 5G, mid 5G, high 5G. Low 5G is already is in use, but if we can use the mid 5G and high 5G, then it will be better for us. That is, the frequency range is higher, so speed will also become high. These are some applications of 5G we can have in future. Like I have already shared that the it is useful for that 5G, sorry, smart city development. It can be used in smart homes, smart energy, healthcare, cars, education, etc. Okay, there is a classification of 5G like frequency band use case, deployment scenario, and others. We will focus on that part only, that is frequency bands, which is important for the designing of antenna. This low band is already is in used, low 5G, mid 5G and high 5G. Um, High 5G is far away. Actually, research is mainly focused on that mid 5G to employ globally that band. So out of these three bands, the mid 5G and high 5G is the current concern for the researcher in microwave domain to develop the antenna. Now, these are some mid 5G band allocation of spectrum. Here you can see in different countries, if we study the total frequency band coverage, can if we can design an antenna from 3 gigahertz to 4.5 gigahertz, we can say we the we develop an antenna that covers the mid 5G band, and we have to also take the concern that the speed should be high. So the primary target is to achieve the band of 3 gigahertz to 4.5 gigahertz in mid 5G band. It is also known as sub 6 gigahertz band because it is below 6 gigahertz. And this is the high 5G band. So if we look at different countries' bandwidth, it is around 24 gigahertz to 30 gigahertz is our target for high 5G. So for mid 5G, 3 to 6, for high 5G, 24 to 30 gigahertz. And some current research gap is there for designing the mid 5G antenna. We have to include high data rates. For MIMO antenna designing, we have to isolate them so that mutual inductance does not take place. That is, one material does not affect the other radiating material. Then we have to design a antenna which can work in both mid 5G and high 5G. In addition to that, if we can develop a reconfigurable antenna, that is one of our topic today, that is, we can switch between mid 5G and high 5G using a single element. That is very, very much challenging because there is a huge gap in between them. That is, mid 5G is 3 to 6, high 5G is 24 to 30. So there is a huge gap. So switching between them is also a challenging one. And finally, a frequency reconfigurable filtering antenna, that is a new term, or in short, we can say recon filter. If we can develop this, these are the current gaps. So using these current gaps, we have uh, I will show these four objectives how they are covered one by one. So first is to design a MIMO antenna only in mid 5G band. There are some tools used. Just keeping them. Okay, so this is my first. I will show four examples. First is to design a mid 5G antenna. Just using that concept, you can also design your own and also publish your work. So this is a design of a CPW, that is co-planar waveguide based two-element MIMO antenna. You can see that from the figure there are two elements, and the ground plane is not below that substrate. It is above the surface. That is on the ground plane. That is why that is co-planar waveguide. That is both the ground and patch is in the same plane. New antenna for mid 5G band having circular polarization. Circular polarization is a property by which the antenna can um, catch any signal from any direction and any plane. So that is a very challenging property. If we achieve this, it will be an extra advantage for us. So let's see one by one. So before designing that antenna, I have already shown these formulas that to design a simple rectangular antenna, that is in design steps one. I have just used the basic formulas to design a simple rectangular antenna. Then I step by step just cut this position, then these corners, then develop this shape. And in design 5, there you can see some rounded shape. These are known as split ring resonator, or say complemented split ring resonator, CSRR. These are, I will explain that. These are basically used to resonate in a particular frequency. And the ground plane is then cut with an F slot to just, this is a technique. Ground plane cutting is a technique by which we can increase the bandwidth. So why I have cut this only F slot, we can also have other slots. So this is also, I will explain in later slides. Now first, see what are the results I have got. This is the S parameter. S parameter is studied to uh, study the bandwidth. If it is below minus 10 dB in that particular frequency, it will work. So mid 5G is for 3 gigahertz to 4.5. So I have just designed it for 4.5. This first design step one. So this one black one is the card for this, where you can see below minus 10 dB there is a if you see this from here to there. So I have designed it for 4.5 gigahertz, but it is around practically 4.8. Now in design stage 2, what I have done, I have cut these two portions and the green line. So here is a resonance and it is coming like, sorry, here is a, we are getting a band, then we are getting a band again here. Not this one. This one is getting above minus 10 dB. Now, after that, these two corners are also cut and this blue one just getting a shift in the bandwidth, nothing else. Then in design 4, again, I have cut this one and almost getting the same. But I have already said that these ring resonators are responsible for generally, these are designed to resonate at two other frequencies. So in design 5, you can see there is a drop. There is a drop that is around 3.5 gigahertz and around 4.2 gigahertz. That is due to the effect of that split ring resonator. And then these ground planes are cut with F slots. I have already what I have said that it is a technique to um, increase the bandwidth. Now you can see in the red line the whole parameter S parameter is below minus 10 dB in my tested range, that is 1 gigahertz to 5 gigahertz, and it is giving a bandwidth of 1 gigahertz to 4.5 gigahertz. So I have reached the mid 5G band. How I have reached these three split ring resonators? I will explain only one of these. Here we can see there is a circle, outside circle and inner circle. The inner circle is in the inner circle, the radius is R2. So what will be the average perimeter? That is L2 is equal to 2 pi R, 2 pi R2 minus S. Why minus S? This cut position is denoted by S. So similarly for outer circle or outer loop, L1 will be equal to 2 pi R1 minus S. From where I am getting two frequencies, F1 is equals to C by 2 into that length L1 into root over of effective dielectric constant of the substrate, and for second frequency similar to the first one. So we are getting two resonant frequencies. And I'm using here a substrate of FR4 that is um, generally low cost and available in the market, and its effective dielectric constant is around 4.4. And this is the equivalent circuit of the split ring resonators. And now I will explain that F slot of this. I have derived this equation in my work that the F slot frequency is due to that F slot will get a frequency in which the antenna will work, that is C by root over of epsilon are effective 1 by 2 into LF plus G plus LF1. So this gap LF1, this total length of LF and this width of G is also very, very important. So these are the explanation that why and how I have implemented this antenna to cover the 5G band. After covering that with one element, I have developed that MIMO antenna, two element antenna, that is antenna 1 and antenna 2, two radiating elements. So it becomes MIMO antenna, that is multiple input, multiple output antenna. This is my fabricated antenna and the antenna measurement setup in vector network analyzer, and this one is in NOH chamber. Now I have just compared that simulated and measured result. You can see S11, that is the radiation, sorry, that is the S parameter of the antenna 1. S22 is the radiation, S22 is the S parameter of antenna 2. So simulated and measured result, these are compared where we can see the S parameter is below minus 10 dB from 1 gigahertz to 4.5 gigahertz. Now, apart from that, we have also studied S12 and S21 parameter, both simulated and measured. What are these? So whenever we are dealing with two element or more than one element antenna, we have to ensure that we have to ensure that uh, the mutual inductance between them should be low. That means one element should not interfere other elements, so they can work independently. In practical, whenever this value is less than minus 20 dB, we can say that is these are very much isolated and these are well isolated and they are not affecting each other. In my research work, here it is less than minus 30 dB. So further no need to improve the antenna um, characteristics. So far, apart from all these, we have to study a few more parameters like surface current distribution. Why I have taken this surface current distribution in 3.3 gigahertz and 3.84? You can see in mid 5G band, we are getting a resonance frequency is around 3.3 gigahertz and another is around 3.84 gigahertz. So we are taking these two frequencies in study to study the surface current distribution here. You can see the maximum amount of current we can find through that split ring resonator. So these are very, very much responsible for resonating that particular frequencies. These are some radiation patterns. This particular frequency in both E plane and H plane showing the co and cross polarization. That co-polarization showing a unidirectional pattern where the cross polarization is showing a very less value around minus 40 dB. So antenna is radiating uh, in that particular frequency in all the direction with good effect. Now I have already said that the circular polarization is a challenging part. The antenna, most of the antenna does not reach, but in that case, it has reached which from circular polarization we can say the antenna can catch any signal from any direction and any plane. The axial ratio is nothing but the ratio of the axis of that azimuth plane and elevation plane. Generally, it is 1, and if we express this in dB, that will be 0 dB if it is perfectly circular polarized. But practically, any value less than 3 dB is acceptable. So in that case, our antenna is showing that axial ratio is less than 3 dB from 1 gigahertz to 4.5 gigahertz. There are some radiation patterns of these antennas, and this is the radiation efficiency is generally nothing but it is a ratio of gain to directivity. Mm, Ideally, about 60% is treated as a good antenna. Here I have achieved a maximum of around 95% as per simulation, and for practically measured value in the stable region, it is around 83% of radiation efficiency is achieved. Now, these are all antenna parameters are studied. After all, these whenever we are studying a MIMO antenna, we have to go for some other parameters also. That is ECC, envelope correlation coefficient, and diversity gain. These envelope correlation coefficients and diversity gains are generally formulated from S parameters also. When for theoretically that ECC should be 0, but practically up to 0.5 is permissible, and similarly the diversity gain 10 dB is the ideal value, but from 9.5 to 10 dB is permissible for practical, and the total active reflection coefficient, that is dark for each element, needs to be studied, and it should be less than minus 10 dB in the working region, and this antenna is behaving well uh, with the given permissible parameters. Then another objective to use the MIMO antenna is to what increase the channel capacity. So we have to study this channel capacity loss too, that is CCL, channel capacity loss. It should be ideally no loss should be there, that is 0 bits per second per hertz. But practically from 0 to 0.4 is permissible. So we are getting a good value here. So it is again a good performer as a MIMO antenna. So after studying all the parameters, some recent works are compared with this, where we are reaching a good radiation efficiency. Isolation is also good, and we are covering the total mid 5G band, and it is also circularly polarized. So these are some conclusions. So from here we can say that after using the basic formula to design an antenna, we have to manipulate or cut the designs in some ways where we have to study the where we are getting the maximum current. We have to cut that portion to getting a more good bandwidth. We can introduce that cutting that ground. We can introduce defected ground structure to increase the bandwidth as well. And circular polarization is also notably a good um, parameter uh, that has been achieved in this work, and this has been published in a journal. Now, what I have shown only mid 5G coverage. Now I will show an antenna that will cover mid 5G and high 5G both. Here you can see the in mid 5G it is 2.9 sorry 3 gigahertz to 6 gigahertz, and for high 5G we have already shared that 24 to 30 gigahertz is our target. So here I will design. I have designed an antenna has that has achieved that mid 5G range from 2.9 to 6 and 26.8 to 29.8 gigahertz in the high 5G band. But what we have to keep in mind, we have to keep in mind that we need to there is a huge gap between these two mid 5G and high 5G bands that we should not interfere with them. Now this is the antenna design analysis where this is a 4-port MIMO antenna, total length of 60 millimeter into 60 into 60, that is the total. Um, Again, FR4 substrate has been used and copper is the radiating element. These are the radiating element that is nothing but a line antenna, these four. And beside there, then the square split tree resonators has been implemented. And in the back side, in the ground structure, this is the ground structure that is split ring, split square, and a defected ground structure of tilted plus symbol has been introduced. But how and why this antenna structure looks like? So there are the different steps. First one is a simple line antenna has been implemented to um, resonate at a particular frequency, and this is the bottom view, fully covered with the copper. Then what happens? We have introduced four split ring resonator, square shaped split ring resonator. In the first work, I have shown the circular split ring resonator, and this is the square shaped split ring resonators, and bottom plane is not altered. Then, in the third step, the ground structure, few portion of the copper is cut. That is defected ground structure (DGS) has been introduced. Then you can see the small ring shape in the four corner has been introduced in the ground structure. So what happens of all these four steps? What and how happens? In the first step, this one is for mid 5G structure, that is you can see 1.1 to 6 gigahertz in the x-axis, and it is for high frequency response, that is 25 to 30 gigahertz. In the first step, it is around 3.3 gigahertz and nothing else, only one resonance frequency, and here in design step 1, nothing achieved, no frequency bands achieved. In design steps 2, what I have introduced, split ring resonator, so it should resonate in more frequencies. So in design steps 2, that blue line that is keeping that 3.3 gigahertz same, and another around 4 gigahertz has been achieved. In high frequency, a small portion of the band has been achieved, but not significantly good. In the third one, again the ground structure has been cut. So bandwidth should be increased as per my first work. So in design steps 3, you can see the bandwidth is increased in that particular region. So the total bandwidth is now around 3 to 5 gigahertz. So my mid 5G is covered, but high 5G not covered. No band, actually, no significant band has been achieved in design steps 3. Now, I what I have done, four square ring has been cut from this ground plane. What I have achieved in the red line, from 3 gigahertz to 6 gigahertz, full band achieved of mid 5G, and in high 5G, significant bandwidth has been achieved around 26.8 or say 27 gigahertz to 29.8 gigahertz. So now after all this optimization, I have achieved both the frequency bands of mid 5G and high 5G. Then after fabrication, I have tested this and compared with the simulated and measured result. Fine, well and good. That is 3 gigahertz to 6 gigahertz in mid 5G and in high 5G around 27 to 29.8 gigahertz. Now I have to study how they are isolated from each other. These are the simulated results, and it is isolated more than 40 dB. So the all the radiating elements, they are not interacting with each other. So this is well enough good. Now these are also has been studied with the simulated and measured result. These are also compared for both 5G band and that high 5G band. Now question comes that the antenna is working well good in mid 5G band and high 5G band, but there is a huge separation from 3 gigahertz to 6 gigahertz and very 24 to 30 gigahertz. There is a in between there is a huge separation. So will that antenna interfere or not? So for this, I have simulated. Here you can see in the x-axis 1 gigahertz to 30 gigahertz are taken into consideration, and we are getting another band in S parameters S11, S22, S33, and S44 that around 16 gigahertz to 21.8 gigahertz. So we are getting a band. So what to do? Now we'll obviously check the whether it is the mutual inductance are good or bad. If it is good, and that is if the mutual inductance is well enough to isolate the antenna, so we can say that will work. But here in mid 5G when it is below minus 40 dB, high 5G is also below minus 40 dB. In practical, below minus 20 dB is permissible. But in that case, the antenna are um, interfering with each other performance. Means one radiating element is influencing another radiating element. So we can say the in that this band in between mid 5G and high 5G, the antenna is not working good enough. So we are not affecting the other bands. So this antenna is suitable for both mid 5G and high 5G band without disturbing the mid band in between them. Now these are some study which we need to study for better performance of the antenna. That is the group delay is well enough or not. That means we are generating more than two elements. So group delay, that's overall delay may impact, but ideally it should be zero again. But practically below 4 nanosecond is permissible, so it is well enough. These are the surface current distribution in one is in mid 5G band, that's 4 gigahertz, and in another it is in high 5G band, that is 28 gigahertz. The red portion is showing the maximum amount of currents are flowing through there, and the blue portion is the minimum amount of current. These are the radiation pattern of copolarization and cross polarization. First two are for 3.25 and 4 gigahertz, and in the C and D for 28 and 29 gigahertz, that is in the high 5G band. Again, the copolarization is very small, cross polarization are unidirectional, so the radiation is also good. It was in elevation plane, and similarly we studied in the azimuth plane. Now these are the gain, the overall gain and efficiency, sorry, gain in both mid 5G and high 5G when it started, and it is going very much, we are giving very much good value of the gain around 4.5 dB. Any positive gain is acceptable, but more than 2 dB is challenging. Over 4 or 5 dB is very, very much good gain for antenna in microwave domain. These are the impedance parameters. These are the simulated value, which is showing the good impedance matching in mid 5G and high 5G bands. These are the radiation efficiency achieving more than zero point 0.9 in the mid 5G, that is 90%. And for high 5G, it is around 80 to 82% of efficiencies has been achieved, that is gained by directivity. Again, like my previous work, the ECC, DG, TARP for CCL, this also needs to be studied for MIMO antenna for a good performer as MIMO, not as antenna, good performance MIMO. That is envelope correlation coefficient ideally should be zero, but less than zero point 0.5 is permissible practically. So we are going well. The DG, that is diversity gain in dB, ideally 10 dB, but any value between 9.5 to 10 is acceptable. Dark is less than minus 10 dB acceptable, which is going good value in both the bands. Mean effective gain, that is MEG, these are also studied from S parameters, and the value is comparatively plus minus 3 dB around is good for new antenna. And again, the channel capacity loss. So we our target is to increase the capacity of the channel by using MIMO antenna. So loss should be zero. Ideally, practically 0.4 bps per hertz is permissible. So we are going a good value for both mid 5G and also for high 5G. These are the comparison of simulated and measured data. And these are some comparative study with the previous works. And so in conclusion, we can say that we have achieved both the bands without disturbing the mid bands and getting a good peak gain around 4.5 dB, enhanced impedance matching, also high radiation efficiency and good performance as MIMO antenna. And its work has also been published in an ECE journal. So in these two works, I have designed a mid 5G antenna, then mid 5G and high 5G antenna is covering. Now we will, all of them were MIMO antenna. But now I will show our antenna that is a single element antenna. Now, no MIMO antenna. It is only single antenna. It will cover both mid 5G and high 5G band, but one at a time. That means it will switch the band. So there will be some switching elements will be there inside that antenna. There is many things written. I will explain in my work one by one. So in simulated view, this is the simulated view of my antenna that is in simple rectangular shape with the fit line that is T shape. That is basic formula has been used. There is a copper guard or say mm, radiating element I have implemented over this T antenna. But you can see there are three elements, switching elements. There's nothing but pin diode has been used. The model is MA4PH301. It is uh, it is very much applicable till 6 gigahertz. That is still the mid 5G band covers. It is this pin diode can be used. But why this pin diode that is D1? There is D2, there's D2. Why I have placed there here? I'm coming to this point. Now you can see in these figures, I have taken the surface current distribution before placing the diodes, pin diodes. First one is for 3.3 gigahertz where maximum current is flowing here. Then for 4.6 gigahertz maximum current is flowing there. And then for 5.5 gigahertz maximum current is just here it is flowing. So I have placed now three diodes here, like this figure, which means at that particular frequency this diode will remain on, and in other frequencies it will be off. So these diodes are biased like these figures, where there is a RFC choke coil is used on bias supply, and whenever this particular 3.3 gigahertz reaches for diode 1, it will get not advanced and it will be kept on. And similarly, for these two frequencies of 4.6 and 5.5 gigahertz, D2 and D3 will be on. Whenever they get this particular frequency, in other frequencies, these diodes will remain off. Now, this is the diode testing parameters where These pin darts has been tested with DC blocking capacitors and these line elements, showing that this antenna is showing that this pin dart is will behave well till 6 gigahertz, because in that particular portion it is getting S1 and S21 are getting these properties are actually the curve getting distracted. This S21 is linear till 6 gigahertz, and this is also getting shifted till minus 10 dB till 6 gigahertz. But after that, this performance gets distracted, so it is good till 6 gigahertz. Now, what happens when these three diodes are on and off in different combinations? So, three diodes, 2 to the power 3, 8 combination will be there. First combination is the mode 0, where all the diodes are off. Fine. When all the diodes are off, it is getting a band within high 5G band is around my 28 gigahertz to 40 gigahertz. You can see the bandwidth in the high 5G band. And is there any current flowing through the diodes? No. You can see that blue lines are there because the diode will work till 6 gigahertz. So in high frequencies, the diode will remain off. Now mode 1, only diode 1 is on. Why? We are passing a frequency of 3.3 gigahertz. Practically, it is we are getting around 3.4 gigahertz. So diode D1 is on and current is flowing through them. No current showing through D2 and D3. So we are getting a narrow band around 3.5 gigahertz. Mode 2 is only diode D2 on, and we are getting a frequency around 4.7 gigahertz. And this is the bandwidth around 4.3 to 4.8 gigahertz. It is also in a sub band of a mid 5G band. Now, D1 and D2 both are on. So around 3.5 gigahertz, D1 is on, D1 is conducting. Around 4.6 gigahertz, D2 is conducting, and we are getting two narrow bands of or sub bands of that mid 5G band. Now only D3 on, we are getting 5 gigahertz resonant frequency, and the bandwidth is around 4.7 to 5.5 gigahertz, and other two diodes are not conducting. Now, mode 5 is D1 and D3 on, so around 3.5 gigahertz, D1 is conducting, around 5 gigahertz, D3 is conducting. Again, getting these two particular bands. In mode 6, D2 and D3 on, so are getting around 4.5 gigahertz and 5.8 gigahertz. And finally, all the three diodes, that is mode 0 to mode 7, that is the mode 7, and the last mode, while all the diodes are on, we are getting three narrow bands in that particular subspace gigahertz band. So this is how these pin diodes are working, and getting a switch between mid 5G and high 5G band, where when all the diodes are off, we are getting high 5G band, and in different combinations of on D1, D2, D3, we are getting narrow bands in mid 5G. So that's how I have achieved both the bands with a single radiating element or single antenna with um, switching with the help of that switching elements of pin diodes. And these are the E plane and H plane radiation patterns and in different frequencies. That is 31 gigahertz, it is in 35. Then in mid 5G, it is 3.5 gigahertz, 4.5 gigahertz. Then it is in 5.8 gigahertz. And these are the efficiency and gain have been studied, where 90% efficiency has been achieved, and more than 5 dB gain in both mid 5G and high 5G has been achieved. All the simulated and measured data are compared in different modes of the switching combination from mode 0 to mode 7. So that is how I have achieved this, and this is the comparison of with the previous structure. And so, in conclusion of this work, I can say that a single element antenna with the help of the mid 5G band is achieved, and in future you also can develop this kind of antenna with some novel features, like I have not I did not get the circular polarization in that particular design. You can achieve this with some other innovative structure as well. And efficiency, there is always a scope to increase the efficiency and gain and improve bandwidth. So you can implement them in future with some different structure, different modeling, and obviously your own novelty. And this has been all this research has been published as well. And finally, I will conclude with that design of another 5G antenna, that is first two element MIMO antenna to cover mid 5G. Then in objective 2, I have said uh, MIMO antenna to cover both mid 5G, high 5G. In objective 3, only one element antenna has been used to switch between mid 5G, high 5G. Now, this objective 4, this is also reconfigurable antenna, but with a band switching. That is a new term you can see here, recon filter. That is reconfigurable and also filtering antenna. So that means the concept of filtering is also introduced in here. Reconfigurable, already objective 3 has been configured. That is switching element introduced. Band has been reconfigured. That is band has been switching. So band switching plus filtering element should be there. So to design this antenna, there are a few steps. First, I have designed ultra wideband antenna. That is a huge band coverage will be there, and there are sub steps like from round shaped antenna. For this is the formula to design a circular antenna, that is resonant frequencies KML, that is the Bessel function to C, like 2 pi r EFF, that is effective radius of the antenna, into root over of epsilon r. For this particular antenna, the substrate has been used as photo paper, right? So defected ground structure is also introduced here. You can see these are the back view or ground structure, and it has been defected here. And also the antenna structure has been modified, and a flower shaped structure has been finalized or optimized lastly. So all these 7 substrates, after optimization, I am getting a bandwidth of 3 gigahertz to 14 gigahertz. So the bandwidth is 11 gigahertz from 3 to 14. This is the ultra wideband, huge bandwidth. And this has been fabricated as well. The simulated and measured results are compared. So I've achieved this band, and there is some radiation pattern has been studied in two resonating frequencies around 4 and 13 gigahertz. Now, in that antenna, first step was to ultra wideband antenna. Now is to introduce the ultra wideband filter design. So obviously for filter there will be two port, input port and output port. And this is the actually filtering element having two different stubs. This one and this one. These are actually important. Stubs are important for filtering. Will come one by one. So ultra wideband filter has been analyzed with different even mode and odd mode. And after all the analysis are done, we are getting a notch band around this C by root over epsilon r effective, that is the effective dielectric constant of that photo paper, into 5 L10 plus L9. L10 and L9 what? This stub length is L10 and this stub length is L9. That is half of this is L10 and this is L9. So if I vary these, if I change or vary this length, the notch band will also vary. Where is the notch band? This one. From 3 gigahertz to 14 gigahertz, we are getting a notch using that filter, that is around 7 gigahertz, that is over minus 10 dB. This value is over here, so it is actually the notch, that is the stop band. And this particular portion and this particular portion, that is covering my mid 5G band, and this is the H band, this is the pass band of the filter. So we need to separate these bands. So for separating this band, in the step 3, we're introducing filter or say filter plus antenna. So whatever antenna I have designed in the step 1 ultra wideband, then I have designed in step 2 the filter. Now I have matched the filter with that antenna. and we discover a new term, filter or filtering antenna. Now, this antenna from 3 gigahertz to 14 gigahertz, it was uh, the bandwidth of the first ultra wideband antenna. Now, due to the effect of that filter, we are getting a notch or say getting a separation between mid 5G and X band, and also this band is also stopped. So, filter has been introduced. Well, so it will also radiate in some frequencies. I have studied this. No changes from the first one, which is good. Now, the final step of this antenna is a recon filter or say reconfigurable filtering antenna. What is that reconfigurable filtering antenna? You can see first I have designed ultra wideband antenna, then filter, then merge this, and now I have used 6 pin diodes here in that stub length. I've already explained this equation that if we can able to change this length, the bandwidth is also changed. So first, I have placed 6 diodes. If these diodes, suppose D6 and D5 are off, so the effective length will get decreased. If the L10 gets decreased, it will get the notch band will shift. That is, it will get increased. So 6 different combinations has been studied. First, all the diodes are on in the combination one. So the effective length remains same. Then in second one, D5 and D6 off. I've already rounded this D5 and D6 off. So this L10 will get decreased effective length. Similarly, in combination 3, D3 and D4 are off. This and this off. So total length will become this only from total. Now for D4, D1 and D2 off. So this will be off. That is smaller stub length will get more smaller. So by like that, 6 different combinations have been used to alter or change the effective length of the stubs of the filter so that the notch band gets shifted. Now we will see what happens of these 6 combination. This is the combination 1, 2, and 3 measured and simulated results are compared. You can see the notch band is getting shifted. Similarly, the bandwidths are also getting shifted. You can see the shifting resonant frequency as well. Similarly, from combination 4 to combination 6, again, all these resonant frequency will get shift. Also, bandwidth will get shift and the notch band will also get shift. So from here, 6 different combinations, we have already said that it will shift. So how they are shifting, you can see from this table in the mid 5G band. This is in the sub 6, X band, and this is in the notch band. That is the notch band is nothing but stop band. So why we will do this? We have applied this due to the different application based antenna. We can only use this particular antenna for different application and for different countries there are different bands in mid 5G antenna. So with different combinations of that switching elements or pin diodes, we can shift the band, we can shift the notch band, we can shift the resonance frequency, so we can use it globally. So this was the main purpose of this final objective of this 5G antenna design. I just shown you these 4 examples. Many more antennas are there. Many more research are still going on in my lab here. But these 4 are I have shown you to as they are linked to each other. I have improved from objective 1 to 2, then 3. So there is always some limitation. Always there is future scope. So I'm going through this. So that is why I have shown today on you these 4 applications. This how crucial this design, how the evolution is going on, how the different elements are getting used to reach the objective for the globalization of this 5G, different mid 5G or say high 5G bands. So similarly, there will be some limitations which it may cover in near future or say in 6G communication, in terahertz communication, we will see in near future, like 5 to 10 years. So many techniques. These are the not, just a small glimpse of that techniques of these four research work. And these are the gain and efficiency in different combination of that switching combination from 1 to 6. Good efficiency and gain has been achieved. So these are the conclusions of final work. This work is also been published. Now, in conclusion, so far in that 5G antenna design, we can say that sub-6 GHz new antenna has been introduced for different applications. Novel 4-port MIMO antenna has also using split ring resonance and different defected ground structure. These are all techniques. You can use it at your own structure, at your own way to achieve what has not been achieved. And innovative approach of that switching of that antenna using pin diodes, and also the filtering element has been introduced to reach more adaptability, reach more applications of that 5G antenna. So in future scope, what you can try advanced technologies using new antenna. Beam forming is one of the current scenario to uh, of the researcher. That is beam forming. That means in rural region or a narrow region, if the beam forming is achieved, it will the more signal will reach in these rural areas where phone towers are quite low, and it will also improve the data rates, reliability, and coverage of all the 5G networks. So beamforming is one of the concern nowadays. Adapting and smart antennas, that is you can what is smart antenna? That is real-time environment that will depend on the real-time environment conditions, that it can be very smart so that it can optimize itself depending upon whatever the condition is. Energy efficient and sustainable designs are also very much in concern. That is to reduce the power consumption in antenna system. Eco-friendly antenna materials need to be developed, and those are all four publications of this work, and those are the references to go through all these research works I have explained. So thank you all who are present here uh, for its listening. If if there is question you can ask for from this. Hello.
Yeah, yes, sir.
Okay, you can ask any question the participant if they have any question.
Dear participants, any doubts or any questions?
Okay. Um, okay, you can conclude here. Sure.
Yeah, okay, sir. Thank you so much, sir, for that highly informative and insightful presentation. I'm surely all participants gained valuable knowledge from your session. To formally conclude today's program, I now invite Mr. Nurani Krishnan, Graphic Designer, Department of Publication and Production, Dynamic Publication and Press, to deliver the vote of thanks. Welcome, sir.
Good afternoon, everyone. On help to on behalf of Dynamic Publication Press, Madurai, I extend my sincerely thanks to all who made this international seminar success. My heartfelt gratitude of our
resource person, Dr. Atanu Chowdhury, for sharing his expert insight on advanced and antenna design for fifth communication. I also thank our organized team, coordinators, and technical support member for the dedicate efforts. Special thanks to all participate for your active involvements and valuable time. Your person has made this every truly and meaningful. Thanks to all once again. Have a wonderful the day.
Thank you, sir, for your kind words. Thank you, everyone, for your participation, cooperation. With this, we officially conclude our fifth international seminar. Have a great day. Thank you so much, sir.
Thank you. Thank you.